When we go to the certain collection implementations in Java, we will need to analyze their time complexities. Therefore, it will be proper to talk about measuring the efficiency of algorithms in advance. When we need to analyze the speed of an algorithm, we need to find some way to do this properly. So, what should we do? Maybe take a timer, hit start when our algorithm starts running, and stop it after its execution finishes. Well, there can be many factors in this measurement. Resulting time might depend on underlying operating system. Maybe some computers utilize more numbers of core and computing power to run the algorithm way faster than other computers, even if the algorithm is not quite efficiently written. So, instead of running time in milliseconds or seconds and measuring it, we need to agree on some other objective way of measurement, which will give general idea for the efficiency of an algorithm. One of the ways to analyze the speed of an algorithm is to look at the number of steps to perform an algorithm. This is called time complexity. Another measurement is memory complexity, which indicates how much memory it takes to run an algorithm. When analyzing the time complexity, we look at the worst case for the number of steps the algorithm takes. Of course, we would like to observe best case scenario, but in reality the best case is not always regular, so it's better to be ready for the worst case scenario. We can also observe average case time complexity, but it still does not give us an upper bound, the absolute worst case result that we can get after running the algorithm. During our analysis, it can be an effective way to compare multiple algorithms when we can compare their worst case scenarios. So the algorithm is a certain sequence of steps to be taken in order to solve a particular problem. Let's say you are programming the vending machine that is applying the number of sugar scoops based on the user input. We can represent the algorithm steps with the following details. So first step, get the cup of coffee, then take the spoon. After this, scoop out the sugar with the spoon, then add the sugar to the cup, and finally check if the quantity of sugar is equal to the user input value. If not, repeat the steps 3 and 4 until it is the desired amount. If we increase the number of sugars in coffee, we can see that steps will also increase, because we will need to scoop out the sugar and add it to the cup as many times as the number of sugars desired. If you only need one sugar, the algorithm will take 4 steps. If the user input for sugar is 2, then the algorithm will take 6 steps. For the input of 3, it will take total of 8 steps, and so on. This dependency is linear. As the number of required scoops of sugar increases, so does the time of the steps performed in our coffee making algorithm. The function for this algorithm can be represented as y equals 2 times n plus 2, where y is number of steps to be taken. And we can exclude both of the 2's in time complexity analysis because they are acting as constants. So 2 will be always multiplied by n no matter how many n we have, and plus 2 will always be present, so 2 will be always added no matter what the value of n is. So it acts as a constant. So the time complexities we are going to meet most often are constant, logarithmic, linear, log linear, and quadratic. The order of time complexities are represented from the best to the worst in this picture, so the constant time is the fastest, and then it worsens as we get below to the quadratic. This graphical representation of different algorithm time complexities is taken from FreeCodeCamp article. You can see the link in the resources section of this video. It shows how different time complexities look like. On the horizontal line we have the number of elements, and on the vertical line we got the number of operations, or also called steps, performed. As we can see, O of 1 is the best, and anything above O of n times log n is considered the bad time complexity. You can also see visually that as the number of elements increase, the growth rate of operations performed is extremely high in case of worsened time complexities, like for example for quadratic and exponential one. So this was an overview of what time complexity and in particular big O notation is. With this fundamental knowledge equipped, it will be much easier to continue our analysis of Java collections in terms of their speed for different operations applied.